In this video, we're going to talk about the term relative velocity and basically try to get an understanding of what's going on, because relative velocity is just a simple way to compare the velocity of one object to another, and it does not always reflect the actual velocity of the object itself. Any of these three cars, we have three cars here in our little diagram. These two are heading north. We'll say going up is to the north and going down is to the south. So I guess we could, maybe right in here, this is, north, this to make these vectors, and then this over here would be to the south. So it's important to understand that when you're talking about the green velocity, the relative velocity of the green car to the blue car is referring to how does this car seem to be moving. The velocity of the green to the blue, G to B, is going to equal what we might say 10 miles per hour south. What does that mean? That means if I'm sitting in this blue car, this car is moving towards me, and it's moving in a southerly direction or in a negative direction. That might be another way of saying that, is negative 10 miles per hour south. And the same idea would be with this green car, the velocity of the, I'll go capital B to capital G, the green car, the velocity of the blue to the green would be 10 miles per hour to the north. It's not just the difference, it's also the direction. Even though they're both moving in the same direction, if we're talking about how they move compared to each other, we just know that this car is moving at 10 miles per hour more than what this one is. So this one's going to slowly move up. This green one will slowly move up to the top, and this one will move just a little bit faster and be able to overtake this car eventually. So those are two relative velocities. The green velocity compared to the blue is going 10 miles per hour to the south. The blue velocity compared to the green is going to be 10 miles per hour to the north. And that's pretty simple when you think about moving up. That's like driving along Highway 41 and you're coming along. You're in the blue car and you're driving the speed limit. Someone's driving a little less than the speed limit. So you come up behind them and you're going to, if you treat this like they're not moving, well, you're going to continue to move in this northerly direction. What about when you're going opposite directions? Well, we have a red car here moving 40 miles per hour to the south. So if I want to talk about the velocity of the red to the green, now I have something else going on. This is going to be a much bigger number. Okay, if I think of this as something that's not moving, this is going to be moving at it at a speed of 90 miles per hour to the south. Because if this car would be considered my starting point, or my sometimes called the reference point, this is going to be coming at it at 90 miles per hour. And you can see down here, the blue car, the velocity of the red to the blue is going to equal 100 miles per hour to the south. Now we notice that even though the cars all had similar velocities, matter of fact the red one had the least velocity of all these cars, when you talk about opposite directions we get greater relative velocities. Right here, 90 miles per hour. That's why head-on crashes are the most dangerous. That's why if this is Highway 41, they're going to have some type of concrete barrier or median or something in between these two lanes of traffic to keep these two things from hitting each other. Because these can be where crashes become, very likely fatal. And they want to try to minimize the forces that basically these impact forces that can affect the passengers. If I want to go just the opposite and talk about the velocity of the green to the red and treat this as something that's not moving and think about these moving towards it, this would be 90 miles per hour to the north, approaching the red car. So between the two cars, the amount of velocity is the same. It's just the total direction that it's moving. Okay, so that's when we're talking about relative velocities. These two cars, if they would hit, and have a collision, let's say this person's not paying attention, they're texting and driving, they might rear-end them with a total collision speed of only 10 miles per hour. Most people have no issues really with that other than body damage of the car. If these two cars hit each other 90 miles per hour or 100 miles per hour, a very different story, and obviously that's not a car crash I hope any of you ever have to experience, because that could be fatal and definitely will probably involve some type of hospitalization. So one other way to look at this is, what if we deal with a different plane? Like now we have just the blue car, 40, I put meters per second. That's a very, very fast speed, but for our purposes, is meters per second going to the north. Not north, but north. Sorry about that. And this is a bird moving to the east. So now we have two planes we have to deal with. We have an x-plane, we have a y-plane. If we go the bird relative to the car, it's going to seem like it's moving in that direction, because that bird is going to be getting closer to our car. You know, if we kind of think of ourselves as a 0 point or our reference point, we have to use some vector addition techniques. So we would have 10 meters per second going this way, and because the bird's approaching us, it would be approaching us at a speed that's equal to our car speed in the y-plane of 40 meters per second, making this total velocity here be total. That was what we were talking about before. This car notices this bird coming at it with a speed in that direction, kind of going down into the right or going to the southeast. So again, to find this, it's a simple right triangle problem because there's all xy plane values. So 10 meters per second squared plus 40 meters per second squared equals vt squared. My total velocity in this case is going to equal 41.2 meters per second. And you know, I could also find out this angle and figure that out a little bit more precisely. I could use a tangent function. Tangent of theta is equal to 40 over 10, and then that's going to give me some angle. That would tell me the angle that this is moving down in. I have not calculated that out, but I'm sure many of you are good enough with the math that you could figure that out. I guess the bottom line is, if you're talking about how the bird moves relative to the car, it's going in this direction. If we want to talk about how the bird notices the car move, well, it's going to go the opposite way. So he would notice the same speed, the same 41.2, but this time moving towards him. And again, thinking of the bird as kind of a stationary point, the car would be moving that way towards the northwest. Again, just the opposite of the southeast direction from before. You won't see a lot of these types of problems in terms of having to find these angles and these sides, but it's definitely a thing to kind of think about when you're talking about relative velocity. The easiest way to keep track is, where's my reference location? In this case, we said it was the car. So the bird is going to seem like it's moving to the south and to the east relative to the car when they cross. And that's our discussion on relative velocity.